Hey students, welcome to class. Today's lesson will be about solving systems by using the elimination method. So far we've learned to solve systems of linear equations in two ways. We looked at graphing, and graphically the solution to a system was, if there was a solution, that is, was the ordered pair or infinite ordered pairs that the two lines share. And then we looked at using the substitution method, which was an algebraic way, which was clearly superior method to graphing, especially when you have non-integer solutions. But sometimes the substitution method is not always the easiest or most efficient way as far as an algebraic method. And so in this lesson we're going to focus on a method called elimination. Now we saw that when we used the substitution method for solving systems, it was really advantageous if one of the equations or both were solved for a single variable. In other words, if, like, say one of them said y equals something or x equals something, and that made substitution very easy. Now, when we want to use elimination method, what we're kind of targeting is systems of equations where maybe both equations are in that standard form, that ax plus by equals c. In other words, where the two variables are on the same side of the equation for both equations in the system. Now, if that were the situation and we wanted to use substitution, we'd have to take one of those equations and put it in either slope-intercept form or solve it for x instead. And so then there's, work that is entailed to do that and possibilities to make errors. And so sometimes it's more advantageous to use this elimination method. And there's basically these 5 steps involved in using elimination to solve a system. They are, number 1, line up the equations. And what we mean by that is line up the x's over the x's, the y's over the y's, and the constant terms together on the opposite side. And the next step would be to multiply one or both of the equations by a number to result in a variable with the same coefficient, or I might amend this to say, or the exact opposite. Step 3 is to then add or subtract the equations to eliminate this variable that either has the same coefficient or the exact opposite coefficient. And sort of what we're doing when we're adding or subtracting is we're kind of like when we add, say, 3-digit numbers. Except for instead of adding like the ones places and the tens and the hundreds places, we add the x's, we add the y's, and we add the constant terms. And in effect, when we have the same coefficient on one of the variables or the exact opposite, and we choose the correct operation, adding or subtracting, what we'll do is we will eliminate one of the variables, and it will produce an equation that just has a single variable that we can solve. Once we solve for the remaining variable, we finally substitute our answer from step 4 into the other original equation, or actually either one, and that will give us the value for the missing variable, the one that we haven't solved for yet. Let's go ahead and take a look at a couple examples and put these steps into practice. Now, sometimes some of these steps are unnecessary, and sometimes maybe we can just start off by adding or subtracting the equations. So looking at example number 1, it says solve each system of equations below by elimination, and then it says identify the solution. So what we said we were looking for is for coefficients that either are the exact same or the exact opposite. Well, in this case, we have coefficients that on the x's that are the exact same. So this is a 1 and this is a 1, so they're the exact same. And so in order to cancel out the x's, we'd actually have to subtract the equations. But that can sometimes be tricky when you're subtracting and you have more than one term after the subtraction. And so what I like to do is I'll take and instead of using subtraction, I'll just multiply, say, the bottom equation by a -1, and basically that just changes the sign. So that original equation stays x plus 7y equals 17, but that bottom equation now becomes -x plus y equals +7. And now, because these are opposites now, they have opposite coefficients in front, all we have to do is add the two equations together, and when we do that, the x's will just cancel each other out. and leave us with 0x. And then when we add the y's together, that gives us 8y. And when we add the constant terms together, that gives us 24. And so now we have a nice easy path to solving. All we have to do is divide by 8, and we can find out that y has a value of 3. Well, now that we know what y is, we can easily find x by taking that and substituting 3 in for y in either one of the equations. Probably the easiest one to put it in is this second equation here. So I'm going to go back to the original, which was x minus y, so it'd be x minus 3 equals negative 7. And so it'd be easy to solve by just adding 3 to both sides. And we can see that our answer then would be x equals negative 4. And then we could check our solution by taking these two values and plugging into either of the original equations. So we could either write our solutions as x equals negative 4 and y equals 3, or as an ordered pair, negative 4, positive 3. So let's designate example 2 as a you try question. So we're going to pause the video and try number 2 on your own and tune back in to check to see how you did. So pause the video now. So thanks for giving that one a try. That turns out to have a solution of x equals 8 and y equals negative 1. And that was actually set up perfectly for adding the two equations and just canceling out the y directly, solving for x first, and then substituting back into one of the original equations to find the y of negative 1. All right, let's look at number 3. So sometimes we are not able, from the original equations, to see a coefficient that's exactly the same or exact opposites, and we have to kind of manipulate them a little bit. So in the case of number 3, you can see that the coefficient of the x in the first equation is 4 and the bottom one is 1, so not opposites and not the same. And with the y's, negative 9 and positive 5. And so adding or subtracting these equations would not eliminate either one of the variables. So we have to do a little work first. So you can target really either equation to work with, and sometimes you have to work with both. And in this case, I'm going to target the x's. I'm going to try to make it so the x coefficients are exact opposite. And in order to do that, I could take this bottom equation here, and I could multiply by negative 4, because that would make the coefficient of the x then negative 4. And so when I rewrite that and distribute that negative 4 to everything, even the constant term, that's going to give me a negative 4x plus negative 20y, or you could write it as, I'm going to write it as minus 20y, and then equals negative 16. And then when we look at that other equation that we just kept intact, the original first one listed, I just simply have to add these, and when I do, you can see the x's just cancel out. When I add the y's, they add up to negative 29y. And then when I add the constant terms, they add to negative 58. And so I could divide by negative 29 to find y, and that gives me a value of y equals 2. And now that I know what y is, I can pick one of the original equations to substitute in for y, and I'm going to pick the second one, but again it could be either one, and that will give me x plus 5 times 2, which is what I found y to be, equals 4. So that's x plus 10 equals 4, and then subtract 10 to solve for x. And then I'll have my complete ordered pair, because x is negative 6, and now my ordered pair is negative 6, positive 2. So I just had to manipulate one of the equations so that I was able then to see that different coefficient, exact opposite coefficient on the x. Now if I wanted to target the y's on the system, I would have had to multiply both equations by something, but that's possible too. But to make the smallest amount of change, I just decided to multiply the bottom one by negative 4. So let's go ahead and designate number 4 as a you try question. So you can pause the video, give number 4 a try, and tune back in to see how you did. Pause the video now. And the solution to you try question 4 was the ordered pair -9, -5/3, or -1 2/3. Let's go ahead and turn the page and look at some more examples. So example number 5. So we always want to take a look and see if it's already set up for us to get started adding or subtracting, and clearly in this example it's not. We have coefficients of 1 for the x and 3 for the x in the second equation, and for the y -1 and -3 for the y in the second equation. And so we've got to do a little work, and we've got to decide which one to target. So I'm going to target the x coordinate. The x coefficient, and I want to make them opposite, so I'm going to multiply this whole top equation by -3. That way I'll make the coefficient of the x -3, and that'll be the opposite of the one in the bottom equation. So when I do that, I multiply that -3 through, I end up with -3x plus 3y, and then the -3 times the positive, or -3 times the -6 is positive 18, and then I'm going to just rewrite that second equation. And now I have these coefficients are opposites of each other, and so I'm going to go ahead and plan to add these equations together. That will cancel out since they're opposites. And so when I add the -3x and the positive 3x, that cancels out. But then when I move on to the next variable, the y's, the positive 3y plus the -3y, those cancel out also. So there's nothing left on the left-hand side. And then when I add the constant terms together, they also cancel out. And that leaves me with 0 equals 0. Well, you may recall when we were solving just single linear equations, when we got a statement like that where the variables dropped out, we had to assess whether our statement was true or not, and that told us how to classify the solutions. And since this is a statement that's always true, 0 is always equal to itself. What that's telling us is that means there must be infinitely many solutions. And if you think what that means in terms of these equations, these linear equations, that means these actually, if graphed, would be the same line. So it would be one line on top of the other, so they share infinitely many points because they're the exact same or coinciding lines. Let's check out example 6. So again, I'm looking to see if the coefficients match up. Okay, I can see the x's don't match up. I can see the y's don't match up. So I'm going to pick one to target. And in this case, because the coefficient, if I say target the x's, I have 3x for the coefficient of the first equation and then 4x. There's nothing I could just multiply, or at least no integer that I could multiply just one of the equations by, so that they were exact opposites or the same. And so I'm going to target both equations. I'm going to multiply both equations by something. And so when I think about 3 and 4, the least common multiple of 3 and 4 is actually 12. So I'm going to try to get them to be 12, one to be 12 and one to be -12. So I'm going to pick the top equation and I'm going to multiply by 4, and that's going to make it 12x minus 36y equals positive 36. And then for that second equation, because I want the signs to be opposites, I'm going to multiply by a -3, and that's going to give me a -12x, and then the -3 times the times the -12y makes a positive 36y, and then the -3 times the positive 36 is -108. So now I'm going to go ahead and try to solve. So I made it so that the coefficients of the x's were opposites of each other. So in order to cancel them out, I'd have to use the operation of addition. And that was the purpose of why I tried to make one of them positive and one negative, so I could use addition. Addition is definitely easier. So when I add, the x's cancel out. And when I add the y's, well, they cancel out as well, kind of like in that last example. But then on the other side, when I add the constant terms, it turns out to be -72. And we end up with a statement here that is clearly a false statement. 0 is never equal to -72, and so the variables have canceled out, and I have a false statement. And you may recall that means that there are no solutions. So that's the empty set, or no solutions. And in terms of a system, what that means is these really must be parallel lines, because parallel lines never cross. There are no shared points. There are no solutions, in other words. So this is a pair of parallel lines. And so say we were to take these original equations and put them in slope-intercept form, what we would see is that they have the same slope, but different y-intercepts, so they never cross. Okay, so to wrap up this lesson, we're going to take a look at some applications where we might use a system of equations, and one that we would actually maybe use elimination to solve. So when we are applying systems of equations into a real life situation, our steps are to first define our variables. So we're going to take a look at our scenario and identify the variables for which we want to solve for. And secondly, we're going to set up two equations. So if we have two unknowns, we need two equations. Later on, we'll move on and we'll look at more elaborate systems of equations where we might be able to handle three variables with three equations and so on. But for now, we're going to be looking at two unknowns that we have to find. And so, of course, we need two equations to solve for two unknowns. And finally, three, we're going to solve the system using our method of choice. So we know three methods now: graphing, substitution, and elimination. So here's our real life situation. Marcy bought a total of 20 used books and CDs during a yard sale for a total of $54.50. If books cost $1.50 each and CDs cost $5 each, how many of each did she buy? So the first thing I want to look at is this total of 20. So Marcy went to this yard sale. She bought a total of 20 things, and they were combinations of books and CDs. So that's an equation I could write that describes these two variables and how they relate to each other. We know that books, say I call them B, and CDs, say I call them C. Together, I'm purchasing, or Marcy purchased, 20 of them. So sometimes when you're writing these real life systems, there's a lot of numbers kind of floating around, and I feel like it's really helpful along the way if after you use a number, you cross it out, because you're not going to use those again. So I already used this 20. I'm going to cancel that right out, and that way I don't get caught up on trying to use that again. So the second thing they tell us is something about the purchase prices of each of the items and the total that was spent. So like this first equation described the items bought, that these were items purchased. Okay, and the next is going to focus on cost. So it's really good to kind of think about the two relationships that are being described. So now this one's going to relate to the cost. So I know that books cost a total of $1.50 each. So along with this B, I could multiply it by $1.50, and that would show me how much money was spent on books. And then the CDs, well, they cost $5 each. So that would be $5 times C. And then this total, so again, I'm using these, I'm going to cross them out. And then there's a total dollar amount. So again, since these are all dollars, they're all going in our cost equation of $54.50. Now that's going to actually give us two true equations that relate all of the things and all of the information that we have about these books and CDs. They're basically like two clues to help us figure out how many books and CDs were purchased. So now we want to take a look and pick a method to solve. Well, this one wouldn't be too bad to use substitution for. I mean, our top equation up here is could be pretty easy to solve for B or even for C. And it wouldn't even be bad to use this elimination method, because if we just multiplied, say, this top equation by -5, we could rewrite it so that the coefficients of this C are just opposites of each other. So if I did that, my new top equation would be -5B plus -5C equals -100. And that bottom equation will stay just the same. 150B plus positive 5C equals $54.50. And now I could go ahead and just add my equations, because since these were opposites here, these are going to just cancel right out. My C's will cancel out. My B's add up to -350 times B and then the constant terms on the other side add up to negative $45.50. And now that's a very easy equation to solve for B. I just simply have to divide both sides by 350, and that'll tell me how many books. And that turns out to actually be 13. So 13 books were purchased, and then going back to the original equations, that clearly the easiest one to substitute this 13 back in for is this first equation. And so we could see that 13 plus C equals 20, and what that tells you is that the CDs must have been 7. Since they purchased 20 items, 13 were books, 7 must be CDs, and that answers our question then. So if we wanted to add our labels, we know that C stands for CDs, and then our B is books. And we've answered our question. How many of each did she buy? She bought 7 CDs and 13 books. Now what I'd like to do is to have you try number 10 as a you try question, and we'll leave number 11 to do in class. So I'm going to leave you number 10. I would like to have you try that one, and we'll actually wait to go over the answers until I see you in class. So we'll look at 10 to see how you did independently, and we'll look at doing number 11 together. So we'll actually end class now with you going ahead and giving number 10 a try on your own. So we'll see you in class.